In this presentation, we will talk about different ways to analyze AC circuits where we may have multiple voltage supplies, we may have a current supply in the circuit, um, or we may want to reduce the circuit down to a single voltage supply and a single resistor. So we start off by talking a little bit about just impedance in general, and then we can talk about how we might convert some sources from one type of source to another. So basically any AC circuit can be simplified as a series circuit that has a resistance and a reactance component. So, in general, we already have done this where we take components that might be connected in series and parallel and we reduce it down to some overall impedance. And that overall impedance would have some resistance associated with it and then some reactive component associated with it. And in general, we can write the total impedance as, that resistance plus or minus that reactive component. So by being able to write down the impedance, the total impedance of a number of components connected in series and parallel, means that we can write them as an equivalent circuit that's in series with having a resistance piece in series with the reactance piece. And that's what this means here, right? So impedance is just the addition of those pieces together. It turns out that we can also take and we can represent an AC circuit as an equivalent parallel circuit that has a single resistor in parallel with a single reactive component. So if that's going to be true and I can take an equivalent circuit that's in series and make it an equivalent circuit in parallel, it has to be true that the overall impedance measured across the terminals has to be equal. But more specifically, that if we figure out this equivalence, it's only valid for a given frequency of operation, since the reactive components depends on the frequency of the circuit. So as we know, this reactive piece for an inductor depends on the frequency and the inductance. In general, the reactance for an inductor is the angular frequency times the inductance, and then for the capacitive part, the reactance is 1 over the angular frequency times the capacitance. So what this means is that if I set up a circuit and I have a particular source that has a given frequency associated with it, and I convert something in that circuit, it's only valid for that particular frequency because the impedance values would change based on the reactance values changing. So the first thing is sort of AC equivalent. We can take components that are connected in series. So I have some overall resistance and some reactance piece that are connected in series. And I can replace that with a parallel resistance which is in parallel with some parallel reactance piece. So in order for these two to be equivalent, the total impedance across the terminals, so if I were to measure the impedance across the series terminal here, the total equivalent impedance here would have to be the same total equivalent impedance as if I measured it across the terminals over here. This Y total that you see is something that we haven't talked about, and I'm not going to worry about talking about it. It's another term that's sometimes used, but it's really not that important to worry about that. So if I look at my series circuit, I realize that in series the components add together, so the total equivalent impedance across the terminals is the resistive piece plus the reactance piece. And I've just put S's as subscript because those are the series pieces. And if I measure across the terminals here, I can combine these two components in parallel. And because I only have two components in parallel, I can find the total equivalent impedance by taking, Z1 times Z2 over Z1 plus Z2, and we've seen this done in other examples. So for the resistive piece, the phase angle is 0, and for the reactance piece, the phase angle is plus or minus 90. Depending on whether it's an inductor, it would be positive, and if it was a capacitor, it would be negative. And then I can write it as the addition of these two on the bottom, again using the plus and minus for the inductor and the capacitor. I'd like to be able to compare these two and say that they are equal to one another, but in order to compare them to one another, I have to be able to compare the real parts with one another and the imaginary parts. So I need to rewrite this and get rid of the imaginary part on the bottom. So what I can do is, the first thing is I can multiply the top together, right? And so if I multiply those, I get the resistance and the reactance, and then adding the angles, I get an angle of plus or minus 90. And then I need to divide by the bottom term. But in order to do this, I'm going to do it a little bit differently. What I'm going to do here is I'm going to rewrite the top portion in terms of the rectangular form. And so the rectangular form of this would be the number out front, and then since this is plus or minus 90, this would just be an imaginary piece, so plus or minus the imaginary piece. Now the reason I'm doing it this way is because I want to be able to take this bottom term and I want to make it real. And the way that I can do that is by multiplying the top and the bottom of this expression by the complex conjugate of the term on the bottom. So what does that mean? That means that I can take the bottom piece right here, and I'm going to multiply the top and the bottom of this expression by the complex conjugate of this bottom term. The complex conjugate just means that you change the sign of the imaginary piece. So I'm going to multiply this by the resistive piece in parallel and then minus plus the reactance piece. And whatever I do to the bottom, I have to also do to the top. So now I'm going to basically FOIL this out, and I'm going to see what I get. So when I multiply the piece on the top by the resistive piece, I'm going to get the resistance squared times the reactance, and it's imaginary, right? So that's the plus or minus j. When I multiply the imaginary pieces together, j times j is a -1. But when I multiply the plus minus with the minus plus, I also get a negative. So plus times minus is minus, minus times plus is minus. So I'm going to end up with an overall negative sign out front, plus a j squared, which is negative, and it becomes positive. So the real part of this is just the resistance that's parallel multiplied by this reactance piece squared. And then on the bottom, when I FOIL this out, the terms that are the imaginary parts are going to cancel, and I just get the resistance piece squared and then the reactance piece squared. And I could go through the same process. Plus times minus is not plus times minus. Plus multiplied by minus is minus, minus multiplied by plus is minus, and then you have a j squared. So I get this term right here. All right, so this is what I end up with. So now I want to figure out how this series circuit can be equivalent to this parallel circuit. And so it has to be that the total impedance that we found for each of these has to be equal. So what has to be equal is the real parts have to be equal to one another, and the imaginary parts have to be equal to one another. So making that comparison, I see that the resistance in series has to be equivalent to the parallel resistance times the parallel reactance squared over the sum of those terms squared, square root, not square root, just squared. And the reactance piece in series has to be equivalent to this term here, which is the reactance in parallel times the resistance squared parallel over this the sum of the squared terms. So essentially, if I had components that were connected in parallel, I could replace them with components in series as long as I use this conversion, and I would still have the same equivalent resistance across the terminals. Without going through all the algebra, you could solve for the resistance in parallel and the reactance in parallel in terms of the series components. And if you did that, you would find that if you were given the series pieces, you could find the parallel components in the same fashion. In this term, it's slightly different, but we could figure out how to do that. And I'm not going to go through all the algebra of how to solve for those. So now we have a way of converting impedance values that are in series to impedance values in parallel, and vice versa. So in the same regard, it was sometimes necessary to have a source that was a voltage source and in DC and converted into a current in DC. And so a real voltage supply always consisted of the voltage supply in series with a resistor. So here a real voltage supply consists of a voltage supply in series with an impedance, and it is equivalent to an AC current supply in parallel with the same impedance. So I could replace any voltage supply that's in series with an impedance across a set terminal with an equivalent AC current supply in parallel with that same impedance, and the relationship between the current and the voltage is just the equivalent of Ohm's law for AC. So these are phasors. So all of these expressions would be phasor notation. So the current here may not be in phase with the voltage over here based on what this impedance value is. So if you recall from DC circuits, oftentimes you had more than one voltage supply in the circuit, and there were a few different methods that you could analyze the circuit in that case. And one of those methods was called mesh analysis or branch analysis, and then another method was called the superposition principle. So we're going to look at mesh analysis in this case and how you can apply mesh analysis for AC circuits. So suppose that I had a situation where I had two AC voltage supplies connected in my circuit, and they are not connected in series or parallel because I have these impedance values that are in between. And for this particular circuit, at this stage, none of these impedance values are in series or parallel because of these voltage supplies. So it turns out that we can follow the same steps that were used for resistors with DC voltage supplies, and we can use the equivalent of Ohm's law for AC and all the equations that are in phasor notation and apply Kirchhoff's voltage law around each of the loops. And so the steps are actually exactly the same as what we saw before. So the first step is that we have to make sure that all of the sources in the circuit are voltage supplies. And in our particular picture, I don't have any current supplies, so we're in good shape. I don't have to do anything. But if there was a current source, I would need to convert it to a voltage source in order to use mesh analysis. Step 2 is to label the current direction in each of the loops of the circuit. So I would look at the voltage supplies here and here, and I might choose my current direction based on the polarity of the voltage supply. And so in my case, for this picture, I am choosing a current direction around the loop on the left to be in the counterclockwise, and also on the right to be in the counterclockwise direction. And I base that on the polarity of the voltage supplies. But if you choose the other direction than what I chose, it's absolutely fine. You will still get the correct answer. It would just be, the phase angle might be different because that would imply a different direction. The next step is to label the polarity of the voltages across each of the components based on the direction of the current. And so just like resistors, if you follow the direction of the current, you go from plus to minus across those components. So across the impedance, it would be plus minus in the direction of the current for the first impedance. When I go across the second impedance value in the direction of the current, I would be plus minus, and then I'm sort of back to where I started. And then I would go around the second loop, and I actually started here. So going in the direction of the second loop, I would have a drop across impedance 2, and then it would rise across the voltage supply, and then I would have another drop across impedance 3. After you've identified the current direction and the polarity across each of the impedance values, then the next step would be to apply Kirchhoff's voltage law. Now, in the meantime, I have also went ahead and I have written down the impedance values in terms of their polar form, right? So in terms of their size and their angle, and these were given to us in the problem, and these were just calculated based on the rectangular form, or the fact that I have, with Z1, I have a resistor, and I must have a capacitor there because I have a negative reactance value. And Z2, I have zero reactance, so this is all resistance. And then for the third one, this must be an inductor because it's positive reactance. So step 4 is apply Kirchhoff's voltage law around each loop and then solve the simultaneous equations. Now, what makes this a little bit more challenging as compared to DC is that we have to make sure that all of our values are in phasor notation, and so doing the math is just a little bit more difficult, but not impossible. So I have my picture that I had before, and what I'm going to do is I'm going to go around loop 1 and I'm going to sum the voltages around loop 1 and set them equal to 0. So I'm going to start at this location right here, and as I go across the first voltage supply, I have a rise, so that's my E1. I have a drop across impedance 1, and that's the current times the impedance. And then I get to Z2 and I have a drop across Z2 due to the current I1, so current times impedance, that's my voltage drop. But I also have a rise across Z2 due to the current in the other loop and the direction of that current. So I have a rise across Z2 from current 2. Now I can actually plug in all of the values in phasor notation, so I know that the voltage is 5 volts with a phase angle of 0. I'm trying to solve for the current in each of my loops, so I don't know I1, but I know what the impedance 1 is based on the values that are given. I know the impedance 2, and I know, and I don't know the current, and then same thing, I don't know current 2, but I know impedance 2. So now I can combine like terms. So I'm going to move this voltage essentially to the other side of the equation, or more generally speaking, I actually am moving the currents to the other side of the equation, making this positive, positive, and then negative. So moving this over and then combining terms, so 3 and the 1 gives me a 4, the minus 3 and the 0 give me a negative 3. And then, of course, I have the current I2, and then I have its impedance value. So I'm going to now convert these into polar form. So I have the voltage is the current times some impedance in polar form minus the current I2 times some impedance in polar form. So this is my first equation. And I have two unknowns, I1 and I2, and I can't really go any further than that, so I have to look at the second loop. So I'm going to look at loop 2, and I'm going to go around this loop here, and I'm going to do the sum of the voltage. Some of the voltages are equal to 0, so I have a rise across E2. I have a drop across impedance 3 in the direction of the current I2, so it's the current 2 times the impedance. I have a drop across impedance 2, so it would be its current I2 times the impedance, but I also have a rise from the other side current, and so that would be I1 times its impedance value. So now I can go ahead and I can plug in the values that I know for all of the impedance values. So I know my voltage, I know my impedance Z3 and Z2, and my unknown values are the current I2 and I1. I can rearrange this and I can move terms around. I can combine the I2 terms together, so I have 2 and 1 gives me a 3, 4 and a 0 gives me a 4. And when I rearrange things, I end up getting another expression that involves the currents I1 and I2, both unknowns, and then I can write these values in terms of the polar form of the impedance that is being multiplied by each of the currents. So now I have another equation, and it has the same two unknowns, I1 and I2. Now what I've done is I've just rearranged this so that the current 1 comes first in this expression and the current 2 comes afterwards. So step 5 is to solve these simultaneous equations, keeping in mind that these equations are phasors and have to be treated as such. So method 1 is just to use traditional algebra to solve for the unknown. Unknown is spelled wrong, sorry about that. Variable from one equation and plug it into the other. Now, the way that you may have learned to do this in the past in terms of DC is to create a matrix, and you can create a matrix and use matrix notation to solve simultaneous equations. And certainly if you know a lot about matrices and you wanted to do that by hand, it would work here. But most of us probably learned how to do this using our calculators and setting up matrices. Now, the issue is with trying to use matrices here is that most calculators will not allow you to put in complex numbers into your matrices, to build a matrix with complex numbers. So if you have a TI-84 and you try to make a matrix out of this, it just won't work. If you have a TI-89, I think it might work, but you have to really know how to use it. So we're going to use the traditional method, and we're just going to go ahead and brute force solve for one of the variables in terms of the other, and then plug that into the second equation and then solve. And so there are other ways to do this in terms of determinants of matrices, but I think for the sake of time we'll just do it this one way, and we'll work with that. So solve for current 1 in equation 1. So that's what we're going to do. We're going to take the first equation and we're going to solve for what the current 1 is, and then we're going to plug it into the second equation. So the very first thing I would do with equation 1 is I need to isolate that current. So I'm going to add this term to both sides of the equation, and I get the 5 volts plus the I2 term is equal to I1 multiplied by the impedance that was equivalent here. The next thing I'm going to want to do is I'm going to want to isolate the current I1, and so I would divide both sides by 5 ohms, phase angle of minus 36.9. In order to do that, well, I guess in order to do that, I can just I can divide each term. So 5 volts, angle of 0, divided by 5 ohms, angle of minus 36.9. 5 over 5 gives me 1. And then 0 minus 36.9 gives me 36.9. Plus I2, 1 over 5 is 0.2. Ohms over ohms, no units. And then 0 minus a 36.9 gives me a 36.9. So I have my current, and I've solved for the current in terms of that term that had the voltage in it and I2. So now I'm going to take this current value that I found, and I'm going to plug it in up here into equation 2. So I start with equation 2, and I'm going to take this expression, and I'm going to plug it in up here for that current. So this is equation 2, 5, phase angle of 0 minus a negative I1. So everything in the large parentheses is my I1 value that I found here, multiplied by the term 1 ohm phase angle of 0, and then plus my I2 here. So now I have an equation that only involves one variable, my current I2, and I need to solve. So here's my starting point for that expression. I want to solve for I2, so I'm going to multiply 1 ohm phase angle of 0 times all of these terms. And so if I multiply 1 times 1, I get 1 volt. 0, 36.9 gives me 36.9. And then there is an overall minus sign out front, right? So that's where this minus sign comes from. And then I have I2, 0.2 times 1 is going to give me a 0.2. Same thing with the angles, I get 36.9. This minus sign, again, factors through and I get a minus here. And then I have plus my last term. So I want to isolate I2, so I'm going to move this term here with the voltage to the other side of the equation by adding it to the other side. And I'm going to factor out the current I2, and so when I factor that out between these two terms, I have this 0.2 ohms phase angle of 36, which had a minus sign in front of it, there's that term, plus 5 ohms, 53.1 angle. I need to add these terms together. So if I'm going to add them together, they have to be in their rectangular form. So I convert everything into rectangular form, all of the terms. And then I can add. So if I add these in rectangular form, I've got a piece on the left, 5 plus 0.8 is 5.8, and then I get 0.6. And then when I add the terms here, I get another complex number in its rectangular form. I still want to solve for I2, so in order to solve I have to divide, so I need to convert everything back into polar form first. So I've converted each complex number on each side into its polar form, and now I can divide. So I can take this term and divide by the other side, and once I divide, 5.83 divided by 5.65 volts over ohms gives me 1.03 amps, and then 5.9 minus 59.8 gives me a negative 53.9 degrees. So I now know what my current is in the second loop. That current is 1 amp with a phase angle of minus 53.9. So now we need to solve for current 1 by taking the expression that we found for current 2 and plugging it back into the results from equation 1. So we have our current I2 that we solved for, and now we need to go back to the equation 1 when we solve for current 1 in terms of current 2, and we can plug this value in. So I can go ahead and I can plug in the value for I2 into the expression. And I have two complex numbers in polar form. I can multiply those two values together, and I end up getting the term that was out front, 1 amp, phase angle 36.9, and then 1.03 times 0.2 gives me 0.21, and then when I add the two angles together, I get negative 17 degrees. Now my goal is to figure out the current, so I need to add these two numbers together, which means I need to convert them back into their rectangular form. And so I have each in their rectangular form, and now I can add them together in their rectangular form. And then finally I can convert that back into their polar form. And I find that my current in the first loop is 1.13 amps with a phase angle of 28.4. So I've used mesh analysis to determine the current in each one of my loops, I1 and I2. And I used this for the case where I had two voltage supplies in the circuit. And if I needed to find what the current was through that middle branch where I had the impedance 2, I would have to take into account that these two currents that I found were actually going through that impedance value in opposite directions. So the current through that middle branch would be the difference between these two. And so basically everything that you learned in DC about mesh analysis is still valid here. Instead of resistors, we have impedance values, and all of our voltages, impedance values, and currents are all phasors, and we have to make sure we add, subtract, multiply, and divide using this complex notation.